Hello, thanks for your interest in this work. In this talk, I'm going to show you some fundamental limits of mobility management today and how to reduce its failures by an order of magnitude in extreme mobility. Extreme mobility scenarios have been a norm rather than an exception, such as high-speed trains, vehicles, and drones. Compared to the static and low mobility scenarios, these extreme mobility scenarios involve much faster climb movement in the wild environment. Many extreme mobility scenarios use 4G LTE and 5G mobile network for anywhere, anytime network access. The mobile network is the only wireless infrastructure that offers wide area mobility management. 4G and 5G deploy radio base stations or cells to cover different geographic areas. As the client leaves one cell's coverage, it will be migrated to another one to retain its service. This is called handover. The handover today is mainly driven by the wireless qualities. It has three phases. In the triggering phase, the serving cell configures the client to measure all its neighboring cells' wireless quality. Once it receives the client's feedback, the serving cell moves to the decision phase. It runs its local policy to decide if more feedback is needed and if handover should start. If a handover is decided, the serving cell moves to the execution phase by sending handover command to the client. Then the client will disconnect from the old serving cell and connect to a new target cell. So in summary, the mobility management today takes wireless quality as input, relies on the client-side wireless feedback, and decides the target cell based on the local wireless-driven policy. So as you can tell, the mobility management should be reliable enough to guarantee always-on internet access. But is it? Although it works fine in static and low mobility scenarios, we find the answer is no in extreme mobility. We have conducted large-scale impact study over Chinese high-speed rails. We found that on one hand, the handovers are more frequent in extreme mobility. It happens every 11 to 20 seconds, depending on how fast the client moves. But different from static or low mobility scenarios, handover failures arise with learning frequency. The failure ratio increases from 5% to 12% as the client moves faster and faster. That means every 3 minutes, we will see a network failure on high-speed train. So why is mobile network today not reliable? The fundamental problem is its wireless-driven design. The client movement causes multipath fading and Doppler frequency shift, which lead to dramatic wireless dynamics. The communication theory tells us that the wireless channel remains stable in a very short duration, which depends on the Doppler frequency shift and therefore the client's movement speed and radio frequency. So the faster the client moves, the more dynamic the wireless quality would be. With dramatic wireless dynamics, the handover signaling can be easily lost or corrupted over the air, which results in handover failures. Even worse, such wireless dynamics can propagate failures to the mobility management. At the triggering phase, such wireless-based feedback can be sluggish. For successful handover, the client should deliver feedback before it leaves the serving cell's radio coverage. But in reality, it may not always be able to do so, because to make proper handover, the client should measure all candidate cells. But for wireless feedback, this means the client has to measure them sequentially, which delays the handover decisions. Reducing the cell to measure can mitigate these late handover failures, but at the risk of missing better cells and causing out-of-service failures. This is a fundamental dilemma between exploration and exploitation. Moreover, the mobility management can also suffer from the complex wireless-driven policy in decision phase. For better radio coverage, mobile operators deploy cells on a different radio frequency bands. To manage them, most operators adopt multi-stage policies. The neighbor cells on the same frequency as the service cells are measured and stacked first. Only if no intra-frequency cells are available, then the policy will consider the inter-frequency cells. The reason is that inter-frequency measurements will waste more radio spectrum and slow down the data transfer, because to measure this cell, the client should resynchronize to a new radio frequency band during which it cannot send or receive data from the old cells. So when there are no available intra-frequency cells, extra round trips are needed to enable this inter-frequency cell measurement, during which the fast-moving client may have left the serving cell's radio coverage and lost network access. Our study has shown that a client on the Chinese high-speed rails takes about 800 milliseconds on average to generate feedback from all cells, during which it has moved 78 meters along the rails, so it's too late for meaningful handover. The fundamental dilemma is that inter-frequency measurements force existing policies to balance the spectral efficiency and decision latency. Of course, the mobile operators know such high failures in extreme mobility. To mitigate late handover failures, they have adopted proactive policy to start handover early before neighboring cell is better than serving cell. However, this approach doesn't work because it raises policy conflicts. When all cells adopt this policy, neighboring cells' handover conditions can be simultaneously satisfied, Then client will oscillate between cells and eventually offset the operator desired failure mitigation because now the client will move back to the old cell. Because of this proactive strategy, policy conflicts in Chinese high-speed rails is 30 times more than those in static and low mobility scenarios. So how can we make the extreme mobility reliable? The fundamental solution is to get rid of this wireless-based mobility management. To this end, we relax the coupling between wireless and mobility and shifts to the movement-based mobility management. Compared to the wireless with short coherence and dramatic dynamics, the client movement is slower and predictable by nature that's more reliable to drive the extreme mobility management. So we propose RAM, the first such solution in the delay-Doppler domain. RAM designs a signaling overlay on top of existing mobile network's physical layer. This overlay exposes the client movement information and helps refine all phases of mobility management. To understand it, let's first look at some foundations of delay-Doppler domain. A wireless channel describes how radio signals from center propagates along multiple physical paths and combines at the receiver. It can be characterized in multiple ways. 4G and 5G measure their OFDM channels as a function of time and carrier frequency. Instead, the delay-Doppler domain describes the wireless channel in terms of the multipath geometry and Doppler frequency shift. RAM places its signal traffic in this delay-Doppler domain. To deliver the signal traffic, RAM converts them from the Doppler domain to OFDM symbols in the time frequency domain using the OTFS modulation and symplectic fast Fourier transform. In this way, signals from the delay-Doppler domain are multiplexed over the entire radio carrier frequencies and time slots, which are now more resistant to signaling loss and corruption. With the delay-Doppler overlay, RAM next parallelizes the cell's feedback for fast handovers. The key is to relax the dilemma between exploration with more feedback and exploitation with fast feedback. We observe that for better radio coverage, a base station in reality usually operates multiple cells on a different radio frequency bands. These cell signals traverse the same paths, so they have similar channels in the delay-Doppler domain. Instead of measuring these cells sequentially, RAM measures one cell per base station only, extracts the multipath profile from this measurement, and then use it to estimate the quality of other cells from the base station without measurements. This is called crossband estimation. How to do that? We prove that we can factorize one cell's delay-Doppler channel estimation into three matrices: a delay orthogonal basis, a path attenuation diagonal, and a Doppler orthogonal base. The path delays and attenuations are independent of carrier frequencies, so the same for all cells from the same base station. The Doppler shift is proportional to the frequency and differs between cells, but given one cell Doppler for each path, we can derive other cell Doppler shifts on the same path. Then we further prove that we could approximate this factorization with the classical singular value decomposition. So to enable the crossband estimation, RAM first runs the singular value decomposition for one cell's channel estimation, then it derives other cell Doppler shift, and then reconstruct this cell's channel response. For the complete algorithm proof, please read our paper. RAM last simplifies the handover decision policy for less failures and policy conflicts. There are three steps. First, for the interfrequency measurement, RAM replaces the multi-stage policy with crossband estimation. This achieves one-stage policy with less round trips and bypasses the dilemma between spectral efficiency and decision latency. Next, with stabilized delay-Doppler signaling, RAM can eliminate many unnecessary configurations and events in today's policy. Please read our paper for more details. Last, with RAM, there's no need for operator to adopt the proactive policy for failure mitigation. This prevents most policy conflicts in extreme mobility. Moreover, with RAM's policy simplification, we can achieve much simpler rules for provable conflict freedom. We have prototyped RAM in commodity software radio and open source cellular protocol stack. We evaluated with 2-year Chinese high-speed rail traces and standard multipath channel models. Compared to 4G and 5G today, RAM eliminates policy conflicts and reduces failures by up to an order of magnitude. Now, even in extreme mobility, RAM achieves comparable failure ratios to static and low mobility scenarios. In achieving so, RAM still retains marginal system overhead. It reduces the average feedback latency from 800 milliseconds to 200 milliseconds. Its crossband estimation has less than 2 dB estimation errors for more than 90% of measurements. It greatly reduces signal loss and corruptions in extreme mobility, so it's more reliable for handovers. In summary, we show that movement-based mobility management is promising for reliable extreme mobility. We present RAM, the first such solution in the delay-Doppler domain. It relaxes the coupling between wireless and mobility. RAM is just the first step to demonstrate the promise of this approach. Besides reliable extreme mobility, movement-based design in delay-Doppler domain can also benefit many other tasks, such as channel prediction, performance boosting, and many more. We wish for more community research efforts to explore them. Thanks for listening. I'm happy to take your questions.